So I recently got the chance to work on this cool, rare laptop from the 1980s. It won awards for its design. It was one of the first with a battery and a hard drive, making it a real laptop and not just a luggable, but I'm getting ahead of myself. Let's back up for a second.
A couple of months ago, I saw this video from LGR, and to be honest, it was really hard to watch.
Oh, this sucks.
The video walks through what is one of the most painful examples I've seen of what shipping can do to old electronics.
Do we even have a power switch anymore? This is where it plugs in.
But this was no mere careless seller. The plastics in the video were so degraded they snapped like potato chips, and it reminded me of a video I did modeling and printing a new case for a Toshiba libretto with a similar problem. Before even thinking about what an effort it would be to restore this rare 80s laptop, I reached out and set in motion what would be a massive project. Now, don't get me wrong, I've modeled and printed reproduction laptop cases before, but this is a different beast. In all of the previous cases, I actually had multiple examples of the full case to model, so it was essentially an effort of making a detailed copy. This case is essentially in too many pieces and too many parts are missing to simply put it back together. So it will be like recreating an image from a jigsaw puzzle with half the pieces missing. And as luck would have it, a friend of the channel reached out who is a legitimate material scientist and has access to an electron microscope, so we're going to try to get down into the reasons why plastics go brittle and others don't. And this won't just be a showpiece either. The goal is to create a faithful reproduction case that is fully usable, upgradable, and to produce highly accurate models for those in need of a partial or full restoration. Now before we jump in, I want to thank Bamboo Lab for sponsoring this video, as a build this serious needs some serious equipment. More on them later, but for now, let's see what we have to work with. The first step in any project like this is to tear it down, get it down to the component pieces and see what you're working with. In this particular case, a lot of it's been done for me in a destructive manner, but there's still things that we need to be careful to make sure that we don't damage as we're removing the rest of the components. As I'm working through this, I can see that this case has definitely been into before, and we see a lot of bends and cracks, a lot of which probably came from the initial damage, but some of them look like just normal wear and tear over time. As I'm taking off this riser card for the ISA slots, I see that this is actually where the CMOS battery sits, and luckily it doesn't look like it's leaked. Keeping on the lookout for anything strange, this power supply cable looks like it has one wire that's been deliberately severed. The key is to determine which of these cut cables and traces are there because of damage and which were deliberately added. Don't worry, little guy, this one wasn't your fault. So far, we can tell that the condition of the electronics is far better than the condition of the case. There wasn't one piece of plastic I came across that wasn't damaged in some way. Part of the teardown process is learning how the case functions. This bar, for example, acts as a handle and a riser to prop the case up. It's clear that this metal plate helps stabilize and protect the circuit board from damage, but it's also going to be a really great tool to use as a template when we're remodeling. I'm also seeing a lot of mismatched screws, which happens over time. Taking a look at the power supply, we get an idea of the range of voltages that are required that might help us to troubleshoot any issues down the road. Now, this came to me in multiple shipments to help protect the plastics from getting further damaged, but opening up a pure box of shrapnel was definitely an eye-opening experience. It is difficult to see anything in this kind of shape, but especially something this old and rare. And I'll be honest, I'm really not one for jigsaw puzzles, but hey, if the situation calls for it. What we're trying to do with these pieces is not to look at them individually, but as part of a larger whole. We're looking for hints about the pieces that we don't have, anything that communicates the design language, corner radiuses, thicknesses, angles. All of these elements, along with some images that were sent over from a viewer who actually has one of these things, are really going to help us fabricate a brand new case. So with all of the electronics sorted out and a pile of shrapnel on the table, it's time to design. Now, when I start most of my design processes, I usually get the same kind of question: why don't you use a 3D scanner? Now, it's probably less relevant for this specific case because I'm trying to design something not from an existing model, but from pieces, but essentially, I could use the 3D scanner to, say, scan the circuit board and find out where the dimensions are in the screw holes and things like that. The truth about these types of scanners today is that the meshes that they create might be very precise, but they're almost too precise. What I'm going for is to get a solid with simple geometries. Something that is absent of subtle defects and textures and all of the things that you would get from scanning a normal part. And for something this complex, that would be incredibly difficult to do working with what a scanner would output. Oftentimes it would require more work than just using my calipers and building a solid off of those types of measurements. Because the key to doing this is about iteration. It's about iterating and printing smaller pieces that you can go back and do fit checks. Because even if you had a sub-millimeter accurate scan, it's going to print differently based on the type of material and the orientation that you printed in. Now, don't get me wrong, having an accurate mesh scan is incredibly helpful, but it's not going to replace iteration, printing, and testing until you get it right. Going back to the jigsaw analogy, there are some larger pieces that I found that I'm going to try to put back together. Now, it's not because I'm going to try to reuse these, but it's just about understanding the part itself and how it interacts with the other pieces it fits into. Now, the reason why I don't reuse original pieces like this and refinish them is because in the places that I would glue them together, the bonds would be strong, but the plastics are so brittle that immediately outside of those places, it would lead to more cracking and breaking, and it's just not really viable. So the only other option is modeling. And as you can see, when I design something, I always start out with primitives, big blocks of circles, rectangles, squares, and then everything else is a modification on those. Now, some parts are more forgiving because they have large gaps and spaces between the part itself and the components that surround it. Not this keyboard cover though, this guy's a different story. This ends up being my nemesis throughout the project. It sits so close to the keys that if you get something just a fraction of a millimeter off, it'll jam the key and make it not press. And just when you think that you've got something right, you run into integration hell. Something may test fine when it's on its own, but when you start putting it together with other pieces, things shift, and then you're back to the drawing board. So again, it all leads back to iteration. Let's talk about plastics. So Blaze and I set off to figure out what made these specific plastics so incredibly brittle, me with my sheer will and determination, and him with a background in material science and an electron microscope. So I sent him off 2 samples, both from the Halikan, but one that seemingly held up way better than the other. The first images came back and they were amazing. This image shows the fractured edges, and while it looks cool at this magnification, it's hard to see much, but as we zoom in, we start to see micro cracks appear. At 10,000 times magnification, we start to see part of the story. In the most brittle sample, we see these cracks everywhere, but what's causing them? If we zoom in even further on another part of the sample, we can see these voids, pockets likely formed by compounds that have off-gassed. Off-gassing is when certain chemical additives slowly release trapped gases or volatile compounds over time, often due to heat, light, or just chemical instability. Now, when a compound off-gasses within a uniform matrix or a solid material, it needs somewhere to go, so it builds pressure. That pressure acts as a crack initiator, and as it propagates throughout the material seeking escape, it leaves behind a trail of micro fissures throughout the plastic. Now, when we analyze the material around these pockets, we see a concentration of bromine, an additive compound used as a fire retardant. Interestingly enough, we see significantly less bromine in the samples that were more brittle than the plastics that held up better. Look, this is far from conclusive, and it may only be a contributing factor, but one could hypothesize that the concentration of bromine or brominated compounds used back in the day to make plastics more fire-resistant could have actually contributed to their degradation over time. And keep in mind, this tracks with how consumer goods were manufactured. Companies and manufacturers were constantly playing with the right formulation to find the right balance of weight, toughness, fire resistance, color, and other factors as well. They could have used different formulas in even different runs of the same mold. Now, there are other things that we know to be true. Different types of plastics age differently. Polycarbonate, for example, is more affected by UV light than ABS. It's also more hygroscopic, meaning it absorbs moisture from the air, which can shorten its lifespan. But it would seem that brittleness isn't solely determined by the base polymer itself, being a ABS or polycarbonate or others. It's heavily influenced by the additives, the dyes, the plasticizers, and the flame retardants. This was a fascinating look into these materials, and I want to thank Blaze and his company Cubic Labs for reaching out and offering his equipment and his expertise for this project. Now, this is not sponsored. He's just a friend of the channel and an incredibly generous guy. So if you have any need for his services, I'll leave a link in the description of how to get in touch with him. So now that we got a better understanding on why this project came to be, let's get back to figuring out how we're going to fix it. When it comes time to work on the bottom side of the case, we've actually got a couple of advantages. This is the part that's going to give us the most critical outer dimensions of the full case. And not just because there are fewer larger pieces, which means better precision, but because that we have this metal plate that we can actually use to check to see if it fits before putting in the circuit board. Now, the best fitment test is going to be trying to line up the screw holes, and it's going to be less about getting the standoffs right, because as we'll see, those can really shift around and be variable. They're not always spot on. And with these test prints, I can also bring in things like the power supply that will give me a better idea of how the larger components are going to fit within the case. As more of the design comes together, it starts to get a little bit easier as you can start to take references and features from other parts of the model. Now, these things may still need to be adjusted over time, but at least you're adjusting a full wall, for example, rather than a small piece of a wall just for one of the parts. Even with a beast of a machine like the H2D, printing still takes time. That's why one of my tactics is to print smaller pieces of a model, or print something like this, which is a template I can use to check the position of screw holes. Printing something like this template takes a lot less time than it would to print a full case. Now, the LCD screen was an interesting one because when you look at it from the outside, you don't see a lot of signs of visible cracks or damage. But I've done this long enough to know that the outside doesn't tell the full story. And when I start to open it up, I can see that the clips that hold this thing together, most of them are broken. Not only that, when I start to peel away the front label, I can see that the screws have already dislodged from the standoffs themselves. So I guess I get to add this to the list of something to remodel and print too. This wiring setup inside this screen isn't the most elegant thing that I've seen, so I really need to pay attention to see how it all comes together. And we come across our first piece of plastic that doesn't actually look like it has damage. So we got that going for us, which is nice. I also get asked quite a bit if when I'm modeling something, if I take some creative design license or if I try to remain as true to the original model as possible. And the answer is a little bit of both. In general, I want to make sure that the outside of it conforms to the original model because usually I intend these pieces to be drop-in replacements so you don't have to do a full print. But there are things I just know won't work, so instead of recreating display clips, I'm going to create an either new screw standoffs or something a bit more robust. And here's a perfect example of why we don't use plates as templates, because the originals are off-center too. It's no secret that I'm a fan of Bamboo Lab products, but when this project dropped into my lap, it was clear that I needed something a little bit more substantial than my Carbon X1. I knew the case needed to be tough, so that means printing in ABS. I also knew that it needed to be highly accurate, and what that means for me is printing at orientations that are going to require a lot of supports. Because of the sheer scale of this project, I knew that there were a few things that would really shorten the amount of time it took me to iterate. I used the AMS2 Pro's built-in heater in order to keep the ABS dry. That, along with the active heated chamber in the air system, made sure that even my large volume prints printed incredibly smoothly with ABS. And using the H2D's dual nozzle system allowed me to have one print head print the supports while the other print head print the ABS. Not only does it make it incredibly easy to peel off the supports, it also cut my print time in half. So with over 300 hours and more than 12 plates in my project, if I didn't have the H2D, I'd probably still be printing. Speaking of, let's get back to it. Even with the substantial build volume of the H2D, I need to print in multiple pieces. I'm using an adhesive that creates a molecular bond so that it ends up as one solid piece. I'm also taking a little influence from woodworking by using bow ties to connect them together and align the part. When it comes to supports, the taller a piece is, the more rigid it needs to be to prevent defects, so I actually build in my own supports into the model that I then need to sand away after it's done. This helps minimize warping and defects for a material like ABS and gives you an incredibly good tolerance. You can see the combination of the organic supports that are generated and the large fins on back that I use to make sure the part is really stable. It kind of amazes me how precise these old laptops are, and so I'm doing a lot of iterations to make sure that everything is lining up just right. Unfortunately, some of the things to go are this embossed text that just don't work at the angles that I need to print the parts at. Each plate takes about 10 to 12 hours to print, so it's incredibly expensive in both materials and time if I need to go back and make a change or a tweak. Using a dual nozzle system and having one printhead that's always loaded up with the support interface material makes printing incredibly fast. Without it, I'd probably be looking at about 20 hours per plate. Now the second step in joining two large parts is filling the big gaps. And because I want this to be as tough as possible, I'm using an ABS slurry, so I will be filling the gaps with more ABS. With a simple mixture of acetone and some old failed prints, you can create a paste that will do a great job at filling gaps but will also molecularly bond to your ABS print. Depending on the thickness of the slurry, it may not get into those fine, tiny places, but this is the first step in filling any large gaps with something that's actually structural and not just cosmetic. As you start to integrate the pieces together, you're going to find problems, and now's the time to take care of them. After you have single parts that are completed, now is the time to start the finishing process. Usually for me, this starts with a sandable filler primer, sanding that down, and then adding on some Bondo spot putty for any imperfections that were too small for the ABS slurry or too big for the sandable filler primer. And you're also going to miss things like these holes in the top side of the keyboard. And while I will go back and update the model, it's a lot easier for me to take care of things like this on the part itself rather than having to go through and print and sand and prime again. When it comes to paint, I use a company to help color match existing parts, but I don't just care about the color, I care about the texture too. Normally, textures are imparted on the mold itself, but we're going to have to do it within our paint process. So I tested out a few different types of texture, and then I sanded those down and put the color on top to hopefully get to something that matches. The only problem with this process is that you end up with an embossed texture that stands out rather than in, which makes the part a little rougher than the original. Now obviously that's a huge nitpick, but this whole channel is about learning and refining your techniques. But at the end of the day, when you can step back and feel proud about your work, that's what it's all about.
Okay, so it wouldn't really be a polymatte video if batteries weren't involved. The first thing we need to do is replace this CMOS battery from this old barrel-style one that could leak at any moment. Now I've got a holder for a 2032, but I don't know if it's actually going to fit when we put it in the computer. I prefer the holder styles because they're easily replaceable, but yeah, that's not going to work. We're going to have to go with a soldered-on version. And when you're replacing any battery, always make sure to replace a rechargeable with a rechargeable, otherwise you're going to have a bad time. This one was a bit snug, but hey, it worked. And now we deal with the beast, the main battery of the laptop. The metal box is definitely a temperature sensor, but we need to figure out what kind and if it still works to know if we need to replace it or if we can reuse it. When you're working with NiCad batteries, you always need to make sure that you're keeping yourself protected. Always wear gloves and a mask, and use a mild acid to clean up like a vinegar solution. I'm going to be using NiMH or nickel metal hydride sub-C cells in order to recreate this battery, The sub C is the type of cell that was used in the previous one, so these should be a perfect match. I'm also going to be printing an enclosure in ABS to make sure that everything is really packed in there and there's no movement within the cells that could damage the connection in between them. I was able to determine that the metal sensor is actually a thermal cutoff and not a thermistor, which I had originally thought. After testing, it looks good, so I'm just going to reuse it and finish packaging up this, well, pack. I originally wanted to reuse the connector as well, but I'm seeing serious signs of corrosion. So I got my JST kit out and made a brand new connector. And checking to make sure I had everything wired correctly, just like the old one. So I get to finish buttoning this thing up and doing a final check on the voltage, and it looks like we've got a brand new main battery. The keyboard. Keyboards are one of those things where it's kind of like a necessary evil. I really hate cleaning keyboards, let's just get that out of the way, but what I absolutely love is having a clean keyboard, so this is one of those things where I just kind of have to grit my teeth, get out the soapy water, and just go at it. As Clint pointed out in his video, these look to be Mitsumi mechanical miniature yellow switches, which it's pretty cool to see a laptop this old have mechanical switches. Now, before people get upset about me using a vacuum cleaner directly on this board, there's no memory, there's no logic, there's no components that would be sensitive to an electrostatic discharge, so the vacuum cleaner was the right tool for the job. I'm just going to replace this tape that was kind of holding down and giving a little strain relief to this ribbon cable, and then we'll continue on. Now, I don't really like to retrobrite or light bright things because it exposes plastics that are already brittle to new UV radiation, and so while cosmetically it turns out great, you know, it's not necessarily good for the plastics, but these weren't the case. With a little bit of soapy water, these things turned out great, so they really didn't have any yellowing. And again, this keyboard cover continues to mock me, so we're going to have to figure this one out. With this kind of build, I can't not make something that's custom. But when I customize something, I don't want to alter the original, so I'm constantly looking for ways to maybe replace a part or a component with a custom piece rather than modifying the original piece itself. And I think one of these side doors is going to be just the thing. I've milled out a replacement door in walnut, and then I've used my laser in order to carve my logo and a little bit of a polymath reproduction badge on the side. So you can use this door, you can use the original, but it's just a nice little piece. I had this idea in my head about creating a brass inlay on a walnut strip that would go above the keyboard. A lot of laptops in this period had these legends that would go above the keyboard. They were used as a reference for certain applications that had different shortcut keys, but I'm going to create my own using this piece of walnut veneer, and then I'm going to put the brass inlay underneath and kind of sand it down and polish it up. I'm using the same design file to, 1, mill the brass logo, but then 2, cut out the hole in the veneer where the brass is going to come through from the bottom. It looks a little rough right now, but once I get the brass in there and sand it down, it's really going to clean up and look good. I just need to make sure to trim off the sides so that I have these little tabs that can insert onto the sides of where you're supposed to put the keyboard legends. I'm going to use the same black walnut finishing wax that I did on the door to really tie both of them together. So the badges of the Halikan were actually in pretty good shape, and I'm going to preserve them. I'm going to send them back to Clint, but one of the things that I really wanted to do is to kind of tie it all together by creating my own and milling them out of brass. The original badge had the text raised up a bit, so I'm going to do the same. I'll then go and paint it, sand the high areas down, and use my laser to add text by ablating or removing the paint. Still needs a bit of polish, but they're looking pretty good. Taking all of the component pieces and putting them all together is by far the most fun and the most rewarding part of the project. It's really only at this point when things start to look and feel like an actual product. rather than just a bunch of 3D prints in various forms of sanding or painting or finishing. It's also a bit nerve-wracking because at this point, when everything starts to come together, you may find that you may have to go back and redo a piece that you thought that you'd completed. And there's always differences in what you wanted to get done versus what you did get done. For example, I had fully intended to reprint my own front face sticker for the display. But as luck would have it, the printer that I had on order never showed up. So at the last minute, I stripped all of the adhesive off of the old sticker and added some new and put it back into place. During a routine check, I also noticed that all of the right power wasn't getting to the floppy and the hard drive. There was a blown fuse on the 5-volt rail that I ended up replacing, and honestly, this could have been the reason that Clint wasn't able to get the hard drive working, because you heard it spin up, but that only requires 12-volt power. All of the logic is powered by 5, so if the 5-volt rail wasn't working, then it could have caused those issues. The original speaker was long gone, so I quickly wired up a new one. Even though I knew full well what this thing was, that it was essentially just a 3D print, it really felt like I was assembling an old laptop. Now, it definitely wasn't easy to get here, but screwing in all of the screw holes and having things fit just right is a really, really good feeling. I was able to source another disc bezel for the one that had turned to goo, and I used some flames in order to reduce some fading that had occurred over time. I reinstalled it on the original floppy drive, and so now the disk and floppy drive are ready to put back in. As I'm putting everything back in, I'm checking the fit and finish of all of the parts of this, making sure that everything is nice and secure and fitting really well. Almost forgot. It's funny, I usually try to figure out how to assemble a laptop by first disassembling it. But with this project, it kinda came disassembled already, so I had to figure it out the first time as I was putting everything together. I can't say that this is not a difficult laptop to assemble or disassemble, but it is kind of involved, and it really doesn't make things like swapping hard drives or disk drives easy, as you kinda have to take apart the whole thing. Getting all of the ground leads connected appropriately is very important with this laptop, otherwise you could hear some artifacts, some humming from the power supply, or some issues with the display or the speaker. These replacement rubber feet aren't really the right color, but they were what I had on hand, and I wasn't able to find any that were a closer match, so we're just going to go with that. Now really the only thing left to do is to install the badges and that really cool custom keyboard inlay. And just like that, the Halikan is back. Now, what I'm not going to do in this video is really put this thing through its paces, but I do need to test it before sending it back, so I think probably the most appropriate thing I can do is try to load up Wolfenstein from one of Clint's own shareware disks. Unfortunately, it just refused to run. So I decided to bust out my Wi-Fi modem, jump online to some bulletin board sites, and browse the files just like it was 1989. It looks like replacing the fuse on that 5-volt rail was just what we needed for the hard drive to get up and running again. I've been using it now for a few hours, and I think we can call this one a success.
I am incredibly happy with how this turned out. The colors are spot on, the case is fully functional and true to the original, at least as much as I could possibly figure out from the pieces and images. We were able to get the hard drive fully working, and for its age and what this machine has gone through, I'm amazed that the electronics were in such good shape. This was the first time where I was really able to dig in to try to find out what makes some plastics hold up while others just turn to dust. I want to thank Clint for trusting me with this rare beauty, for Blaze for the time and equipment and expertise, for Bamboo Lab for sending over the H2D and for the continued sponsorship of this channel. But mostly I want to thank you, my viewers. You were the ones who blew up Clint's comments section and let him know that I might be up for something as crazy as this, and well, kind of worked out. If you liked this video and you made it this far, I assume that you did, please remember to like and subscribe and send me a comment. It plays a huge factor in YouTube deciding to push my channel and my content to a larger audience. And if you're interested in seeing more over-the-top restorations, maybe check out the time when I restored a super rare IBM ThinkPad that looked like it went through a wood chipper. Thank you so much for watching, and we'll see you in the next one.